The question was, since the course will be mostly over Python projects from here on out, will the final cover Python topics? Yes, to a large extent. Yeah, it's going to be a lot of Python. You can sort of expect it's going to be kind of a multiple choice. It's going to be a multiple choice test. There's going to be a lot of definitions. So, for example, we're going to spend probably the first 10 minutes of the lecture here going over some definitions. A lot of it will be kind of really simplified review of things that we've talked about already in this class, but we're going to kind of hit them again. You should expect, questions about the definitions. It'll be pretty boilerplate, multiple choice test. But yeah, a lot of it will be over Python projects. There will probably be no more writing out equations by hand in this course. So, Edward asks, is the SPR discussed in the ThinkDSP book? No, it is not. But I found a different book that goes over how to sort of picks up and works with the SPR. It's written in MATLAB, though, so one of the things I'm going to do over the break is transcribe it to Python. So that'll be fun. Okay, let's go ahead and get going today. Thank you for joining me here in the lab. By the way, I've got this fan. It's like 80 degrees in my lab. So I've got this like fan running. If it the class before said they couldn't hear it in the audio. So I just want to make sure if you guys start to hear some static or some weird stuff caused by this fan, please let me know and I'll turn it off and sweat it out for you guys. So let's get into it. So like I said, today it's going to be a little bit weird. The next couple of days are going to be kind of strange because we are going to, or like I said, we're doing this hard right turn. We're going to focus more on doing applied work in Python. I think it's going to be, like I said, it's going to be a lot more fun. It's going to be a lot more beneficial. You're going to get a lot more experience doing the stuff in Python. We're going to use a library that makes a lot of the stuff pretty easy. But there is a sort of fair amount of backpedaling or backstepping that we got to do. We got to sort of take a step back to go forward. And in fact, what we're going to do today, for those people who are taking this course in the spring, this will be the thing we do on the first day of class. I'm going to start here next semester. So you guys are going to get to be my sort of guinea pigs for this new curriculum moving forward. So what will be the back half of the class for you guys will actually be the first half of the class for the guys in the spring. And then for the back half of their class, I want to do the software-defined radio stuff. So I apologize if you feel like you're missing out, but there's nothing I can do about that. Okay, let's go ahead and get started. The first thing we've got to do is kind of eat our vegetables a little bit. We're going to talk about we got to get some definitions going, right? We're going to start the book. First off, the textbook, that ThinkDSP book. Let me pull it up on Amazon. Flip over here. So it's this book by O'Reilly. If all of you guys are probably familiar. Well, maybe not since Stack Over, in the days before Stack Overflow, these like Wiley textbooks or these O'Reilly textbooks with animal on the covers were like the reference that you used. They're like the greatest books in the universe. But anyway, this one is ThinkDSP. It's all about just doing digital signal processing in Python, and that is the book that we are going to focus on. And a lot of stuff we're going to do, we're going to take it one chapter at a time, just kind of working out of this book. It's on Amazon. You can get a paperback for like $24, or you can get a Kindle version for like $15. You don't need it to move forward. I'm going to do everything here in class, and I've typed up the exercises from the end of the chapters for you guys in Blackboard. But if you want to grab a copy of that book, it's so far I really like it. It's pretty fun. I will mention though, it is not written for electrical engineers, right? It sort of takes kind of a little bit more of a simplified approach to some stuff. As you're going to see when we do some of these definitions, they're a lot more simplified, which maybe you might prefer. It's not overly academic and gross. So all of that being said, let's go ahead and, oh no, spoiler alert, I'm going to use this and then type the stuff. So let's go back to this other one. Because I'm going to look at that monitor and then type the stuff over here. All right. So the first thing we're going to do is we're going to come up with some definitions, right? These definitions, just commit them to memory. They're very simple definitions. They're easy to memorize. They're going to make great multiple choice questions on the final exam. So just make sure you know the terminology. That way we have a common language as we move forward through the textbook. And a lot of this is going to be review. A lot of this is going to be stuff that we've already talked about. And I'm going to go ahead and type instead of writing and not subject you guys to my terrible handwriting. So periodic signals is the first thing that they're going to talk about. And there's like I said, a handful of definitions. Let's do this. The first one is, what is a periodic signal? No, so for you, I mean, you can. I always like to write stuff down just as a memorization tactic, but notice that these are all here in the content library of our class notebook, so all of this stuff will just be here for you. So you don't need to type them if you don't want to, if you just want to hang out and watch. I promise we'll get to the, it's like you said we weren't going to have to do anything. We're just going to write Python code. We'll get to the Python code eventually, but we're going to get these definitions down first. A periodic signal is a signal which repeats itself after some period of time. See what I mean? They're very like layman's, very simplified, casual definitions after some period of time. Next up is a sinusoid, which is a periodic signal which has the same shape as the trigonometric sine function. You guys have all seen sinusoids. You're very familiar with sinusoids. They are, you know, sine waves. We won't spend too much time. We're just going to get these definitions knocked out as fast as we can. You're also already familiar with period. The duration of each cycle of a periodic signal. And the frequency is the number of cycles of a periodic signal which occur every second. Then it's measured in hertz, which is abbreviated HZ. All right. Periodic signals, sinusoids, period, frequency. Like I said, I know that you guys already know this. I just want to give you guys the official definitions that we're going to use. That'll show up on the test, and so that we know what we're talking about when we use words moving forward. So that's period, that's frequency, such as this, right? So we're going to make the distinction between a signal and a waveform. A waveform is the shape of a periodic signal. And the distinction is important. Full screen that. Okay. The shape of a periodic signal. And then we have a thing called the timbre, right? We briefly mentioned it when we did that Python synthesizer project. And timbre is our perception of the quality of a sound, which is determined by the waveform. So a sinusoid, so for example, up here in this example, let me try still kind of figuring out my new workflow here. But I think I can draw and have it show up. Yeah, look at that. Anyway, so for example, the waveform is a shape of a periodic signal, and the timbre is our perception of that sound that's made by a waveform, and it's determined by that shape. So for example, this is a 440 hertz sinusoid. So a periodic signal which has the shape of a trigonometric sine function. So here's, I guess I need to type or write. Here is 440 hertz played by a violin, right? They are both, so 400 hertz played by a violin. Let me get that grossness out of here. .440 hertz. Sinusoid, so 440 hertz sinusoid and 440 hertz played by a violin. They're both signals that are 440 hertz, but notice that one is a clear sinusoid and one is kind of a messy mix-up sinusoid. And notice, but if you were to hear both of these, so Akil asks, so how does the timbre affect the Fourier transform of the signal? It's because that's going to, in fact, they would be the same. In fact, the Fourier transform, as we're going to see in just a second, would reveal the timbre, right? So there's all of these sinusoids in here. Now, if you were to hear this, you would hear 440 hertz, which is the a middle C, right? Or no, excuse me, it's a natural A. And it's the music note, 440 hertz. These would both sound exactly the same, except you would be able to tell the difference. One would be like a tone, and the other would be the sound of a violin playing a note. The difference comes from the waveform, again, the shape of that periodic signal. And we're going to sort of uncover how that works by looking at, the Fourier transform of that signal. Which takes us to our next thing here, which is spectral decomposition. And we have some definitions here. Such as, first, hey, good, I'm glad you're liking it, Akil. So the definition of spectral decomposition is that it says that any signal can be expressed as the sum of sinusoids with different frequencies. I need to change this default. So, spectral decomposition tells us that any signal can be expressed as the sum of sinusoids with different frequencies. So both of these are 440 hertz periodic signals. One is a sinusoid, one has a messy waveform, but this waveform is created by a bunch of different sinusoids all lined up with each other. Next up, we need the word spectrum. Spectrum is the set, right? Often we think, we sort of lazily just sort of refer to the spectrum as, well, it's the frequency spectrum. It's all the junk that's in there. But more definitively, spectrum refers to the set of sinusoids that add up to produce a signal, right? So the collection of individual sinusoids is the spectrum itself. To reveal that, to perform or to sort of visualize the spectral decomposition, we use the discrete Fourier transform. Or the DFT. We're going to define that as a mathematical function which takes a periodic signal as input and produces its spectrum, or the spectrum, as output. So it gives us, we give it a signal, such as this 440 hertz played by a violin, and the discrete Fourier transform, the DFT, will produce as output the spectrum. It will tell us what sinusoids are present in that 440 hertz violin signal. Then we have the fast Fourier transform, or FFT, and this is just an algorithm for computing the DFT. So what we're doing is the discrete Fourier transform. When we actually do it in code, we're going to use an algorithm called a fast Fourier transform. And there are all kinds of weird variants of the fast Fourier transform. So if we were to take this violin recording and compute its discrete Fourier transform to reveal the spectrum, we would get this. Let me blow it up just a little bit. All right. So this shows us all of the sinusoids that are present in the signal, present in the spectrum. So for example, or actually not for example, in actuality, the x-axis shows the range of frequencies that make up the signal, and the y-axis shows the amplitude of each frequency component. So we can see there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It keeps going on and on. Different sinusoids, and we can see what the amplitude of each individual sinusoid is, which I think is pretty cool. And there's some definitions to go along with that. There's the fundamental frequency, which is the lowest frequency component of the signal, right? So whatever is the lowest piece, such as this one right here, is going to be the fundamental frequency. In this case, it's that 440 hertz. Then there's the dominant frequency, which is the frequency component of the signal, which, there we go, I can just make that bigger, has the largest amplitude, right? Whichever one is the biggest, that's the dominant frequency. It's also the one you're going to hear if you're listening to it. And often, in fact, almost always, the dominant frequency is also the fundamental frequency. So that lowest component, so they're not tied together, they're not the same thing. The fundamental frequency is the lowest one, so that's this one, and the dominant frequency is the one with the highest amplitude, and almost always, but not always, the fundamental frequency and the dominant frequency are the same thing. And then finally, that leaves us with what we call the harmonics, which are the frequency components, the sinusoids, which the frequency components besides the fundamental frequency. So in our diagram here, we have the dominant frequency, which is the highest amplitude. It's also the fundamental frequency. It's the lowest one. And all of the rest of these are just sort of grouped together, and they're called the harmonics of the spectrum. So that is it as far as our definitions here. Are there any questions about any of those before we move on to actually doing some code? Cole asks, so if 440 hertz is the fundamental frequency, 80 hertz would be a harmonic? Yeah. The harmonics are also going to be multiples of the fundamental frequency. So you just double them. In fact, in music, they're always going to be multiples. If you have harmonics, if we start mixing signals together, then we're going to get weird stuff. You'll start seeing harmonics in the spectrum itself that aren't multiples of the fundamental frequency, but that's because of the presence of other signals. They're going to be multiples of something. So I guess a better answer would be no, it's not always multiples, but if you just have one waveform, then yeah. And that's kind of a messy answer. But almost always, especially for the purposes of what we're talking about right now, when we say harmonics, they're going to be multiples of the fundamental frequency. Okay. So we are going to use in this, so that's this. Don't forget, all of these notes are just right here in the lecture notes on Discord. Or not on Discord, but on our class notebook in OneNote. And let's quickly go over. We're going to use a Python wrapper that came with the book. The guy that wrote this book also wrote a Python library, and he put it on his GitHub for ThinkDSP. What you need to do is you need to download this library. So it's github.com/Alan Downey, which is the author of the textbook, /ThinkDSP. And he's going to have, he also has like all kinds of textbook stuff and like figures from the textbook, but also he has the code, and he has his own, his .wave files, he has all kinds of good stuff, but most importantly for you, he has the actual thing itself, the ThinkDSP.py, the Python library that you need in order to do the stuff. Yeah, let me post the, that's a good idea, Bashir. Here, I'll post it in the chat. Boom. So make sure you download that and use it. There's a couple things that we have to do before we can get things going. So this is, there are all kinds of cool data science tools and signal visualization tools that are used to do these sorts of things. He basically just created a wrapper that makes it a lot easier, but we still need to install the dependencies. So what we're going to need to do is use terminal or command line or whatever it is that you use. I like to use PowerShell 7, and to install, Python libraries. Don't forget you use pip. You can't use pip to install ThinkDSP. He hasn't included it as a dependency, but you need to include these other things. So if you want to view the Jupyter notebooks, you need to install Jupyter. You don't have to install that one, but you definitely want to install NumPy, SciPy, Pandas, Matplotlib, and Seaborn to do the visualization. So over in PowerShell, really easily, you would just type, pip, NumPy, SciPy, Pandas, Matplotlib, and Seaborn. Oh, I'm stupid. It's pip install all of those things. And it's going to say, hey, you already have all those things, because I do. But if you didn't have them, it'll install the ones that you're missing. So there we go. Any questions about installing the dependencies using pip in the command line? If you've made it this far in your computer engineering education, I'm going to assume that you know how to use a command line or PowerShell or the terminal. So let's see, that's that. And then usually it's a good idea to go ahead and just clone the repository. So in GitHub, code, download the zip. And then what I've done is I've just gone ahead and grabbed the two files that matter. And anytime you're going to use, so for example, we're going to do some demos right now, called it lesson 1, and I went and copy and pasted these two files, the ThinkDSP and the ThinkPlot. And actually, I don't need the ThinkPlot. Make sure when you're doing the assignments to, even though I have and the TA has the ThinkDSP source file, if you would just go ahead and include this thing in your directory with your code files that you submit in your assignments, that'll just sort of speed things up. That way we don't have to copy and paste ThinkDSP into the folder, and everything will just sort of run out of the box. So make sure you've got that ThinkDSP file, and let's go ahead and do some stuff. I'm going to open up Visual Studio Code. You can also sort of flip through the ThinkDSP.py class for all the different classes. So for example, he's got stuff like play wave file and read wave and all kinds of stuff. He's just basically put a wrapper around a bunch of tools so that we can focus on the actual DSP part, not the just Python coding part. So an extra layer of simplicity, I guess. So let's just go ahead and type through the kind of common stuff that we need, that we're going to start with, right, in order to do the first assignment that you have. So I'm just going to call this, lesson 1.py. If we want to do any kind of data visualization, we're going to need the Matplotlib PyPlot library. So from Matplotlib import PyPlot. A lot of people also say as PLT. I don't do that very often because I don't mind typing PyPlot. And then let's do some stuff. So let's talk about signals. All right. So there are a couple of different things. If we want to create a sinusoid, he's provided 2 libraries for us. So we'll say from ThinkDSP import, and right in Python, since I have the ThinkDSP Python folder or file right here, I can just import it directly. I'm going to import, he's got one for cosine, so capital C cosine, capital S signal, makes a cosine sinusoid, and ThinkDSP import sine signal, which is pretty good. So we can create a cosine, we can create a sine. He also has a sinusoid one. But these are pretty common. And if you want to make a signal, all you have to do is just say, let's do a cosine, cosine sig, cosine underscore sig equals cos signal in parentheses. All you have to do is define a frequency and an amplitude and an offset. And if you don't define anything, it'll give you a 440 hertz at an amplitude of 1 and an offset of 0. Well, let's go ahead and type it in anyway. 440 amplitude, let's make it 2 just for the heck of it. And offset, that's that shifting, the phase shift offset of 0. And yeah, let's call that good. And if we want to plot it, the first thing we need to do, so this will create a signal that we can do some stuff with. But if we want to plot it, we need to create a waveform. So we're going to create cosine underscore wave, and that's going to be, it's a method of the signal class itself. So cosine underscore sig dot make wave, and then you say how long you want to make it for. So duration equals, let's do it for half a second. So if you wanted to create a 440 hertz tone, then an amplitude of 2, that's our signal. That's basically the raw definition of our signal. And then we actually want to make a waveform that we're going to visualize, say make wave, and we say for how long we want to do it. So this is going to create a 440 hertz tone for a half a second. And then we just want to plot it. So cosine wave dot plot in parentheses. And then we still have to use pyplot to actually make it appear, which is the only reason we need to import pyplot. We do pyplot dot show. And if we run that, let's see what happens. So I'm using a Python package in Visual Studio Code that lets me just run from the top. And sure enough, we have a sinusoid at an amplitude of 2, it looks like. That goes on for a half a second. Right? We can zoom in on it if we wanted. And we can see that we've got our sinusoid signal right there doing the stuff. Now, when we first created that, it was kind of, I'll run it again, right? It gives us this whole sort of monster piece. Sometimes we don't always want the whole thing, so we want to create a segment. So what we could do is we could create, let's say, cosine underscore segment, and say if we want to look at just a sort of small piece of it, then instead what I would do now is say is equal to cosine wave dot segment, and say I want to start at t equals 0. I want to go for the let's say the period. So if I want to grab the period, by the way, I would say period is equal to, you got to get that from the signal. So cosine signal dot period. And let's say I just want to start at 0 and I want to go for 3 periods. So I would say period duration equals period times 3. And let's comment that out. And now I can plot the segment. So cosine segment dot plot pyplot dot show. Run that, and there you go. Now I'm going to see a smaller little chunk of the signal that I'm working with. So I'm only seeing what it asked for: 1, 2, 3 periods of the signal. Any questions about that so far? It's pretty straightforward stuff. This ThinkDSP library makes a lot of this stuff crazy easy to work with. So that's pretty awesome. Let's go ahead and take a look at mixing signals now. So we can use it to combine signals. So let's create let's create a sinusoid. So I'm going to create it from sine signal. Let's double it. Let's make it a harmonic. Let's make it 880 hertz. So frequency is 880. Let's make its amplitude 1.5, or let's just make it 1 to make it half of it, and then let's make the offset 0. And then if I want to mix them together, so I'm going to say mix signal is just by adding them together. So my original cosine underscore sig plus my sine underscore sig. And that will mix those signals together. If I want to view it, I got to have a waveform. So I'm going to call it mix underscore wave. And that will just be mix sig dot make wave. Well, let's also go for a half second. And then I'm going to call it mix segment. Let's just view a segment of it. So mix dot wave, or mix underscore wave segment. Start equals 0. Duration equals, let's do it the period, mix sig dot period times, I don't know, let's do 4 just for fun. So that should create a mixed segment waveform that we can plot and show. So I'm going to comment those guys out. And I'm going to say mix sig dot plot and pyplot dot show. Let's hit that and see what we get. There we go. So we can see that our signal has been kind of mixed a little bit. We've modified the waveform slightly by mixing that cosine at 2 with that sinusoid or that sine signal at 1, and we get this kind of messy looking signal. So we're able to mix it up and give it a waveform. Any questions about that? There's also a couple of things that we could do, such as sort of shifting and scaling. So for example, if I wanted to maybe amplify it by, I wanted to double it, right? So I would say something like mix underscore wave dot ys. So that's the sort of y scale. And let's say it's equal to times equals 2. So we're going to double it. Let's plot that and see what that looks like. Did that double it? Oh, it's because I did the wrong one. Stupid. Mix seg dot ys equals 2. There we go. Now that bumped it up to 4, so we doubled the amplitude there. I didn't leave that up for very long. We've doubled the amplitude, so we've scaled it up vertically from +4 and change to -4 and change, but we didn't change the horizontal axis. If we want to change the vertical scaling, then we're going to change the TS, so mix underscore seg dot TS. It's going to be the time shifting. So we'll do TS is just going to be equal to, let's do 1.5. And see what that looks like. That's going to shift it over by 1.5. Oh no, what have I done? Did I break it? Can I not do a fraction? Oh, maybe I can't do it that way. That's what happens when you do it live and you don't practice it ahead of time. Let's do this. He says as I'm messing it up. Let's see if we can shift the wave over by 1. Mix wave dot TS equals 1. No, yeah, Akil says pitches the amplitude of the sinusoid. No, Curtis is correct. Pitch is the frequency. The amplitude of the sinusoid would be the volume of the sinusoid, the loudness. Okay, so I wasn't able to time shift the segment, but I was able to time shift the original signal over. So that worked out pretty well. Actually, I need to go up there. The time shifting is like the one thing I didn't practice. Yeah, gain is also a way to do it. Although gain usually refers to how much is changed after the fact. So, for example, here, modifying it by 2, that would be a gain of 2, right? We're actually going to take our signal and multiply it by 2. That would be a more accurate description of gain. Okay. I'm not sure. It's not a lot of reason to do time shifting and Y shifting in the signals. You got to do it in an assignment, so mess around with those. But we're going to move on because we only have about 10 minutes left. I need to get to the good stuff, man. Let's look at the spectrum of things. So, spectrum. So if we actually want to view the Fourier transforms, let's take a look at that mixed wave. And if I want to view the spectrum, all I got to do is just make a spectrum. So to take a Fourier transform using this library, so I'm going to say spectrum is equal to mix underscore wave. Yeah. Dot make spectrum. And then plot it. Spectrum dot plot and pyplot dot show. And there we go. So we can see that, we've got a fundamental frequency, which is also a dominant frequency here at 440, right? So it's sort of showing me on the x-axis that it's, I can't dial it in too great, but it's approximately 440. What if I zoom in? Yeah, so 400 and change, so about 440 there, and then our 880 right there. And it sort of beefs up the amplitude. The amplitude gets kind of blown out of proportion, but we can see that the fundamental frequency is 440, and it's got a harmonic at 880, despite the fact that we created that sort of artificially. So, for example, we had talked about having harmonics that aren't multiples, right? We could get weird, right? So we could make this one like I don't know, let's do something stupid like 973. But let's also make it an amplitude of 3. And run that. So now check this out. I've got still my 440 signal, but now I've created my 970 signal that's also sort of blown up and it's bigger than the original one. So even though this is the fundamental frequency, we've artificially made it such that this other one, this 973 hertz tone, is bigger than the fundamental frequency. So now the dominant frequency and the fundamental frequency are different things. So, but that just sort of goes to show that we can get weird. We can mix some stuff up and get signals. I'm gonna go and change this back though. 1.5. I'm gonna change this back to 880. So come here. Playing waveforms. This ThinkDSP library will also go ahead and just play the signals for you, I believe. So if I just say mix.wave.play, I haven't actually tried this one yet, but I think it will play the signal for me. Nope, it did not. So I need to look into how that works a little bit better. Yeah, I didn't look at that. Okay, forget that. Nix that bit. Well, that should have worked. I'm kind of play is not recognized. Yeah, something weird happened here. Yeah, I'm gonna mess around with that a little bit more. In your assignment, you got to play some stuff, so you're gonna mess around and sort of debug and try to figure out why that is not playing. Well, it looks like it threw a warning. So Akil asked, "So do you still have to normalize the signal?" It looks like it did normalize it right here, and then it threw an error. It said a play is not recognized as an internal or external command. I'll mess around with this after class, and when I figure it out, I'll send you guys an email letting you know maybe this is a dependency that we need to install before we can actually go ahead and play it. But we won't worry about that right now, because I want to show you like the coolest thing so far that this ThinkDSP library does, which is we can do filtering like in one line. So I can define a filter. So spectrum dot, it has built-in functions for low pass, so low pass, high pass, and band stop. So if I want to make a low pass filter, all I have to do is say spectrum.low pass, and in parentheses tell it what my cutoff is. So I'm going to say cutoff is, let's make it 600 hertz, since that's in between 440 and 880. And what our factor is, this is how much we want to reduce it out. So if I want to say I want to reduce everything, factor of 0.01, this will pull out 99% of everything past the cutoff frequency. So if I go ahead and plot that now, there you go, man. So we've done low pass filtering in one line. We're in the future. So you can see there's our 440 hertz that's still there, still doing the thing. And we have a little bitty sort of nub there at where 880 was, but it's all been filtered out. And that's, yeah, man, that's filters, right? If we change this to high pass, we should sort of get the opposite, right? Ooh, yep. So now we've lost most of our 440 signal, and we've got all of the rest of our 880 signal. So that's pretty slick, man. If you don't think that's cool, that we can do filtering in one line with this library, then you're just not having enough fun. Let's see, a couple of just sort of syntactical things. Reading and writing. If I want to make if I want to read in a waveform file, so wave from file equals, I need to import the library for that. So from ThinkDSP import read wave. So wave from file is just read wave, whatever the file name is. And then if you want to write a file, it already comes built into the class, so that like mixwave dot write, and then you give it a file name dot wave. So reading and writing is pretty darn easy to do. And I think that is about it. Any questions about any of this Python stuff that we've talked about? So hopefully you can see it's pretty easy to kind of get up and running, make some signals, create some Fourier transforms, even create some filters, right? That's pretty slick. That's pretty cool. Let's talk about, so we're going to kind of move over, you're going to have Python projects, Python assignments now. So we're doing away with like the handwritten assignments. It's going to be Python exercises, but we're going to go back to that thing where it needs to be due by the next class. So for example, I'm going to pull up the one that I've made for you guys. They're pretty easy. They shouldn't take you more than maybe 15 or 20 minutes to do, like a half hour at most. Let me find the assignment. So here's the one. It's due before class on Wednesday. Go over some instructions. So it says for each of the Python exercises given below, write a separate .py script. So for example, there are 3 exercises here. So give me 3 different Python scripts just to keep them separate. When you completed the exercises, compress all your .py files along with any additional files. So if you used a .wave file, anything you used to make it run, make sure you include all of that in the same folder, zip it up, and then submit that zip file on Blackboard before the due date. Also, like I said, to assist with grading, please also include the ThinkDSP.py file in your submission. That way, I can just open your folder and it'll just run. Some free response questions. Some of these have free response questions that want you to make kind of just sort of general observations about what you're working with. So it says free response questions. Provide answers to any free response questions as a comment at the bottom of your Python script. So for example, if I asked you, a question, you would just sort of, make it a comment. Down here at the bottom, answer to free response question number 1 or whatever, right? So just go ahead and type those down there at the bottom just to get you thinking a little bit critically about what we're writing and what we're working with. And then, yeah, whatever free response questions are given in bold. So exercise 1 here says, go to freesound.org, download a sound sample that includes music or speech or something that has a well-defined pitch. Select a roughly half-second segment where pitch is constant, right? Maybe somewhere where they're playing a long note or something like that. Compute and plot the spectrum of the segment you've selected. And then see kind of what you mess around with it, and then answer this question. What connection can you make between the timbre of the sound and the harmonic structure you see in the spectrum? So listen to it and kind of see, as you mess with it, what happens there. And then use these filter functions, use the high pass, low pass, and band stop functions to filter out some of the harmonics and plot the resulting spectrum, and then convert the spectrum back to a wave and play the audio. And how does the sound relate to the changes you made in the spectrum? Exercise 2 says, synthesize a compound signal. That's basically what we just did, where you created a sine and a cosine and add them together. Evaluate the signal to get a wave object and play the audio. Also compute and plot the spectrum. This is basically what we've already done in class today. Just do it again to make sure that you can do it yourself. And then answer the question, what happens if you add a frequency components which are not multiples of the fundamental frequency? So if you add weird stuff to it, what happens? And then exercise 3, write a Python function called stretch. So write a function which takes a wave object as input and a stretch factor and speeds up and slows down the wave file by modifying the TS and the frame rate. A hint, this will require you to open up, explore the ThinkDSP Py code itself. Basically, this one just asks you to, this one is just going to force you to like open up thinkdsp.py and just kind of mess around with it and read the code and try to find where those things are defined and how they work in the code. So there you go. And that's due Wednesday before class. Akil asks, can we use the Jupyter Notebook since it has built-in functionality in VS Code? Yes, you can do that. You can use Jupyter Notebook. Okay. Any other questions? Okay. In that case, that is all for today. Apologize for keeping you guys over just a few minutes. Yeah, this kind of gives you, I know we kind of took a step back as far as things that we've talked about, but hopefully, this gives you an idea of how the class will be moving forward. Hopefully you enjoyed it. Hopefully you think it's a little bit more engaging, a little bit more fun. And that's awesome. Yeah, so hopefully you like it. If you don't like it, let me know. If you do like it, let me know. I need that feedback before I take it on to next semester. And we're gonna kind of keep moving there. So on Wednesday, this first assignment's due, and we'll do the material from chapter 2 of the ThinkDSP textbook. We'll work through the code and work the examples and look at some exercises. So if there are no questions, comments, or concerns, I will see you guys on Wednesday. Thank you.